Okay, good morning everyone. Welcome to week number 12 of the problem solving session on linear algebra through geometry. So, this will be the final problem solving session. So, we won't be having any extra solving session after this. Okay, so are you guys writing the exam by the way?
Yes, sir, yeah.
Oh, okay.
It's on 1st November.
Oh, it's on first now. Okay, good. Well, you?
Yes, sir.
No, I won't be appearing in exam.
Oh, okay, sure. So, yeah, this time's week I had some different plans. So, I wanted to so since this week is more about applications of linear algebra through applications of linear algebra actually, because even the lectures did not have a geometric angle. So I felt like, looking at the lectures, you can look at those applications, but I thought of collecting some of the applications that um I've seen in my say academic life, and some interesting bits that I can share with you about linear algebraic applications and tools. So that's how I wanted to make this week, but unfortunately, yesterday's incident happened, and I could not do it on time. But thankfully, at least both of you were there to show up. Okay. It would have been nice if the others could also have joined, but I don't have their contact with me. Uh, okay, so that's how I want this week's content to be conducted. Okay, so here's the first one. So here's a simple algorithm that Google supposedly uses to rank its web pages. Okay, just a slight linear algebraic flavor. It's not using linear algebra too much. Okay, but so just let me explain to you the context in which it happens. Is that, let's say, that there are web pages all over the internet, right? And you know, uh, and there are web pages all over the internet. Let's say A, B, C, D, E. Okay. Now, um, you make a search on Google. Okay, and these pages are all related to the same context. You make a search on Google, and then Google will start listing out these pages. And some of these pages may get featured earlier, let's say BC, and some of them may get, let's say, pushed to page 10. Okay, and no one actually goes to page 10 usually. Okay, they just end up with B and C. So Google needs to really make sure that the ones it shows at the top are the best ones. Okay, and well, how it can do it is at first just experimentally show them all the pages arbitrarily, and then according to the number of clicks that the user does. Okay, if a user does more clicks on A, then maybe A is a better page. It should be ranked higher, so you'll insert A here. Okay, instead of B, and push B below. So now A has a rank 1, B has a rank 2, C has a rank 3. Now this algorithm is perfectly fine, but the issue arises, okay, when these pages are linked to each other. Okay, that is that, uh, let's say, um, B can lead to C, and C can lead to E, and D can lead to C, and that's how it is. And let's say C can lead to A, oh, okay, or A can lead to C. Let's say this is how it is. Now, if you notice, even though like more users are clicking A, they A eventually points to C. Okay, and D also eventually points. Let's say B also eventually points to C. Okay, so anyhow, all three of them are pointing to C, and uh, then and they are on the same content. Then it could be so that it looks like C is a better algorithm, but uh, the users are getting to C via A. Okay, that's why there are more clicks to it. Okay, and by the way, these need not be different websites. They could be same pages within the same website also. Okay, and this algorithm is what is inspiring the page. This context is what is inspiring the PageRank algorithm for Google. So the algorithm is actually rather simple. So here is the context in which it is saying. Okay, so consider a miniature web page consisting of three web pages A, B, C. The link structure is as follows: page A links to B and C, page B links to C, C links to A. Okay. Page A links to B and C. Okay. B links to C, and C links to A. And that's it. So this is this is a small example. Now uh, construct the link matrix L where Lij is 1 if page J links to page I. Okay. So Lij is 1 if and only if page J leads to page I. Okay. Now let's create this matrix. And so page J links to page I. So but it's IJ. So let me call it page B, A, B, C, page A, B, C. So this is sort of the transpose of the adjacency matrix. So A does not link to A. Um, B links to no nothing. C leads to A and 0. Okay,
So
and
Lij is equal to 1 if page I points to page J.
no, that's the
Or,
opposite. Page J links to page I.
oh, I see. Okay, all right.
So yeah, it's if you've seen the adjacency matrix of a graph, then it's the transpose, right? Yes, it will be the transpose.
Yeah.
Okay, but I don't think that I think it's just a semantic notation. I don't think that even if you do IJ, it will cause much of a problem.
Okay.
Okay, now you create this. Now what about what is okay? Yeah, this is confusing. Page J leads to page I. So J can be A, B, C. Oh yeah, let's do column wise. That's better. So A links to what others? A links to B and C, right? And let's do this. B links to C and nothing, and C links to A and nothing. This is correct, right?
Yes.
Okay, good.
Sir, I have
Yeah,
one doubt. Here, 2 comma 1 entry is 1.
2
So,
comma 1 entry is 1. Yeah,
okay, so by that, are we saying the latter one
yeah, that's right.
goes to the.
2
Okay,
comma
okay.
1 entry is 1 if and only if 1 leads to 2.
Okay, okay. Got
Okay,
it.
so at least that's how
Yes, sir.
this question is framed. Okay, but yeah, like I said, that's just a semantic issue. Okay, you can equivalently frame it in terms of I maps to J also. Okay, now they're saying convert L into a column stochastic matrix P for where each column sums to 1. Okay, so what you do is convert L into a column stochastic matrix P. Okay, I need to create P from L where each column sums to 1. So I need to make sure that all of them sum to 1. But how will I do it? Well, this is anyways
So,
the first. Oh, sorry, it's column wise. No? Okay. So the first column needs to sum to 1. So what can I do?
So we can take the n degrees into the consideration and like to compute the probability. Like say B is having, so A is having a connection to B, but then to how many nodes A have connection? So if I divide that quantity,
That's right.
then we would be able to convert this into a probability thing.
That's right. That's right. Good. So this is what is called a stochastic matrix. Okay. A stochastic matrix is one where the sum of rows and the sum of columns. I mean, one of them. Okay. If it's called row stochastic or column stochastic. In this case, it's column stochastic, which means that if the columns sum to 1, okay, columns sum to 1, then it's called a column stochastic matrix. For example, here, in this case, it's already summing to 1. And in this case also, it's already summing to 1. Okay. So I don't need to change them. But why is it called stochastic? Stochastic always means that there's a probability involved, right? What this means is, so let me label them A, B, C, A, B, C. What this means is that the page A has a half probability of moving to B and a half probability of moving to C. Okay, if or in this context, if a user is at a page A, then he has a half probability of clicking for the page B and half probability for clicking for the page C. That is what it means. So this is the stochastic matrix. Okay, and yeah, it represents the transition probabilities of a random web server. Okay, now the thing is, now we need to come up with a ranking, right? So here's the thing. Let me come up with an okay. Just give me a moment. So what I'll do is I need to come up with the just one moment. So now I'll have what is called a rank vector. Okay? And the rank vector will look as follows. So it will be, say, oh yeah, okay. It's just the relative importance, right? So I have separately also the rank vector. Okay, so this is RA, RB, RC transpose, and I this guy is let assume it in terms of percentage. Okay, so let's say this is like I have a chance of 23% that it is A, and let's say this is like I'm 50%. Okay, and this is 50 plus 73, that is 22. Oh no, 27. So this is the relative importance of each page. Okay, so what do I mean by that? So if in the beginning I feel like all of these pages are equally important, or I can put some kind of bias in the beginning, but let's say I put all of these as like 33%, 33%, 33%, or I rather write it in terms of 1/3, 1/3, 1/3. Okay, this is what I think, because I don't know in the beginning what is the importance of each of these pages. Now what happens is, but as the user clicks, okay, I realize that, oh, if the user clicks, it turns out that a user clicks on A more, okay, the user clicks on A more, then I'll increase the probability of A. Okay, make it, let's say, 2/3 and make the others 1/6, 1/6. That's what I can do, and it'll change with time. But I don't want to do it experimentally. No, I want to come up with the algorithm there are what are called online algorithms that do it, as the input comes. But I want to prepare this for the user, and then maybe I'll experimentally change it later. But for now, just with the data that I have, I want to rank the best algorithm, best pages. Okay, so here is the idea that the matrix that we just created, okay, which we'll call it P, this matrix, okay, this is what I'm going to multiply with the rank vector. Okay, so let's do it. So 0, half, half. What was the matrix? 0, 0, 1, 1, 0, 0. Okay, so this is what I'm going to multiply with the matrix. 3, 1, 3, 1, 3. Okay, and let's see what happens. So this is PR. Okay, so the first entry is what? 1/3. Right. Second entry is 1/6. That's it. 1/6. And the third entry is large, half. 1/6 plus 1/3. 1/6 plus 1/3 is 1/2. Oh no, 2/6. 3/6, yeah, 1/2. So this is what I have. Okay, so this is my P times R, and let me call it R1. Okay, call it R1. This is it. Now observe something. Okay, uh, what happens if I sum everything in R1, which is 1/3 plus 1/6 plus 1/2.
1.
1.
Yes, exactly. So this becomes 1. So this is a property of stochastic matrix. When you multiply matrices, you multiply with stochastic vectors, because these sum to 1 and these sum to 1. The result is also 1. So this vector is also a stochastic vector, and this is actually my new rank. Okay, this is my new rank. So this means that in in one click, if the user does, okay, in one click, if the user does, he has a and 1/3 probability of getting to A, okay, and 1/6 probability of getting to B, and half probability of getting to C. Right. So it seems like this is a better choice here. Now let's multiply that again. Now this is my new rank now. So C has the highest rank. Okay. Let's do that same thing once again. So we'll do 0, 0, 1, half, half, 0, 1, 0, 0 times 1/3, 1/3, 1/3. Oh no, sorry, the new R. So this is PR1. Okay. So this is 1/3, 1/6, 1/2. Okay. Oh great, Satinder is here. Hi Satinder. Yeah, thanks for showing up.
Oh, good morning, sir.
Yeah, good morning. Yeah, I did not have a way to contact you, so I could not mail. But you got a calendar invite, is it?
Yeah, yeah.
Oh, okay, great, great. Okay, thanks. Okay, so yeah, Satinder, we were talking about the page rank algorithm. I'll go over it, okay, at the end of this. So I'll just continue for now. Okay, so this guy becomes half, and half times this is 1/6, and this is 1/2. 1/6 plus 1/6. So this is 2/6. 2/6 is 1/3. So now that you see, the probabilities have changed. In 2 clicks, we've shifted, we've changed the probabilities now. It looks like A is higher. Now I can keep, so this is my new R. Okay, this is my R2. Now I can keep doing this. Okay, this is also what is known as a Markov chain. Okay, and uh, and every Markov chain, not every, but there are some special Markov chains which have something called a stationary distribution, and that is what we are looking at. Okay, looking for. So what I mean to say is, I can't keep doing this process. No, at some point I want this process to stop. Right, but I want this process to stop and finally give me the page rank algorithm. Now it would be very strange if we are we can do that, Rohan, but we can do something better. Instead of doing this, that's right. Instead of doing this, p to the Rohan is suggesting instead I can compute p to the n. Especially it'll be very nice if it's we've already seen that if it's diagonalizable, if the matrix is diagonalized, then this can be computed rather easily. And if it is not diagonalized, I can do repeated squaring, and I can multiply it with r, and I can compute this. That is right, Ron. So I can take a large n and then do this. So that will save me some time. Now, question is, can you do something? Can you think of something better?
Sir, what is our target? Like better in terms of where do you want to reach?
To get to the stationary distribution, to get to the point that we don't change further.
Okay. So to see whether it comes to a stable condition or not, maybe
Exactly.
some convergence of this kind of thing.
Exactly.
So will it always converge? The first question is this: that for a stochastic matrix, if I keep multiplying it, I just said intuitively that for a large n, if I come up with p to the power n. But my question is, how am I not sure that it will always change and it will come
That's
to
a very good question. That's a very good question. Yes, it need not always converge. Okay. Yes, it may not always converge. That the R that I started with is bad. Okay, but here's the hint now that I'll give you.
Okay.
That this is the sequence of thought I was saying was that R, I start with a particular R, then I start improving the R. Okay. Now the hint that I give you is, you need not start with that bad R. Okay. Can you think of immediately coming up with a good R? Think of some linear algebra.
Oh,
okay.
Okay, right. So if it is an eigenvector, it will never change.
Exactly.
So it will basically scale, and the scaling factor, if you know, so it is very much easy to predict.
Good. So I'll just repeat what Rohan said. So like Rohan said, see, if I started with this, okay, 1 by 3, 1 by 3, 1 by 3, and then I improved it to 1 by 3, 1 by 6, 1 by 2, and then I improved it to this, and I keep going on, and this never stops. It need not always converge to a stationary distribution. That is true. Okay, every Markov chain need not do that. But what I'm saying is that this algorithm, that's the beauty of this algorithm, that it need not do this iterative process only. You can completely avoid it by thinking about what the good R does. Okay, the immediately coming up with that good R. What will that R look like? Okay, so this is one possibility. Okay, and here's the alternative. The good R will look like, if I multiply P with R, I'll get R itself. Okay.
But only if R is an eigen.
Yes, only if R is an eigenvector. That means the rank that we are looking for is an eigenvector, right? For this to happen, to reach the stationary distribution. And what is the eigenvalue for this eigenvector? For such an eigenvector?
1.
1. right? So this is by the definition of eigenvector is lambda x. So in this case, lambda is 1. So here is an application of linear algebra in the page ranking algorithm that I don't need to do this iterative process at all. I don't need to power p to the n. I just need to compute the eigenvector that corresponds to 1. Okay, so we can do that. Let's do that. So what is our this? Um, can we do that directly? I already know lambda. No? Okay, yeah. So I can do it directly. So 0, 0, 1, 1, 0, 0, 1, 1, 0. 0, 0, 1, 1, 0, 0, 1, 1, 0. Okay, this is my vector. And R is, let's say, R1, R2, R3 equals R1, R2. Okay, let me call it.
But then instead of L, you should have taken probability matrix, isn't it? Because we have taken L matrix here.
Oh, sorry. Yeah. Probability matrix. Good. Thank you. P is what? 0, 0, 1, half, half. Okay. Thank you. Half, half. Okay. So here you have x1, x2, x3. Okay. Now let's do it. So x1 equals x1 half x1 equals, what is this? Yeah, x2. And the third equation is half x1 plus x2
First,
equals x3.
in first equation, it should be x3. x3 is equal to x1.
Oh, x3 equals x1. Sorry, my bad. Okay.
Yes.
So this implies that x1 equals 2x2. So 2, 1, 2 is the eigenvector, is what Rohan is saying. Let's see. I can fix x1 as x1 itself. Okay, so what did you choose as your free variable, Rohan?
X3, sir.
X3.
So
Okay, let's do that.
first I calculated, yeah, p minus lambda I calculated, then the null space. From the null space I.
Okay. So this is x2, nothing but x2. So you have 2x2 equals x3. So let's do the same. Let's fix x3 as a free variable. So you have x3. X2 is 2x3, and x1 is 2 times x2, but x2 itself is x3. Yeah, so this is what we have now. And yeah.
Sir, if you take x2 also as free variable, then also you will come to that 2, 1, 2 result, because you have already reduced everything.
No, yeah.
But this seems
It does
to be
not
incorrect,
matter.
no? 1, 2, 1.
Oh,
Yeah.
x1
This
is
one has some problem.
x3. X1
So
equals
x2 will be x3 by 2.
x2 will be, oh, okay. X2 is actually x1 by 2, and yes, x2 is x3 by 2. Yeah, correct. Okay.
Yeah.
So this is what we have. So which is nothing but x3 1 half 1. Okay. And this is your eigenvector, right? So this part, so eigenvector equals 1 half 1. Okay. But we are not getting it in terms of percentages now. So we have some very large values. So what do you do about it?
We can do the normalization kind of a thing, just dividing by the sum of it. So 2 by 5, 1 by 5, 2 by 5.
I would say, okay, 2 by 5. Which norm are you using, L1 or L2?
Actually, not normalization. So we are trying to convert it to percentage, right? The first component, the second component, all.
Yeah.
So eigenvector is 2 1 2. From I just converted that to 2 1 2, not 1 half 1. So 2 1 2 was better looking to me. So I converted it to 2 1 2, and then so 2 by 5 into 100, 1 by 5 into 100, and 2 by 5 into 100.
You
That's how I
can do that.
converted it.
You can do that. I mean, you can do 2 1 2. But I mean, there is nothing wrong with doing 2 1 2, I think. But I just want to observe what happens if we calculate the L2 norm.
Okay. Do we need to calculate the L2 norm here?
No, I mean, it's neater to think of the eigenvector as a normalized eigenvector, standard normalized eigenvector. No?
Okay. Okay.
That's all I'm saying. But it will translate in the same scale. That's not an issue. But yeah, it's okay. We can do this. That's not an issue. So this is what we have. So and but if you normalize this in terms of L2, then you'll get all of them less than 1. Okay.
Yeah,
Rohan?
you said we need to convert it to standardized eigenvector, that is normalized, whose length is 1. So
Unit.
why do we need to convert it to eigenvector, to unit eigenvector?
We don't need it, but it's neater to say that
Okay.
the rank, final rank, is nothing but the unit eigenvector, normalized eigenvector. That's all I'm saying.
Okay.
You don't need to. You already get a feel of what is happening here. And additionally, if you want all of them to be less than 1, that will be helpful.
Okay.
And sum up to 1. Okay, yeah, great. So this is the final ranking that we have, and we can have full faith on this ranking, because you know that if you start with this ranking, you will converge in this ranking. Okay, and for a random user, okay, because the probabilities are chosen uniformly at random, on average, this is how the pages will behave. So the page A and C should be ranked higher, and page B should definitely be ranked lower. Okay, this is one application of linear algebra in a practical scenario. Okay, and that is clear, no? I'll just repeat everything for Satinder. This is clear.
I have one doubt.
Yeah.
So if you start with 2 1 2, then will be in that line only, and the scaling factor will also be 1, because eigenvalue is 1 here. But
no. So
how do we?
Yeah.
Well. Okay. So I'm asking that how do we know that we have to put less rank on B? It might be possible that B is the most important page, and then isn't it the case that we are already deciding what will be the rank of what will be the rank vector?
That's what we did not do that. We did not, because see, in the beginning we gave them equal probabilities, no, and then started going over them. But even this is not an optimal technique to do. What if natively B is such an isolated page that you cannot do this? What is the ideal vector to start with? But here we are assuming nothing about them. No, we are just saying that this is the stationary distribution, and with this ranking you will definitely converge. Oh, but at the same time, by the way, okay, I understand your question. The reason also lies in the probabilities that we chose, that these are chosen uniformly at random in some sense. Okay.
So the matrix P decides actually which page will have most rank.
Exactly.
It is not the rank vector actually.
Exactly.
Okay.
We are removing the user component from the entire.
Oh, right. Okay. Actually, intuitively also we can see that only A redirects to B with half probability. And in other cases, they can go from A to C, both cases, right?
Yeah. Exactly. But if the graph gets very big, like millions of nodes, then that time it does not become important. Yes, go ahead. Go ahead.
I think these probability values are not random, and this is similar to the random walk kind of the thing.
It is similar to it is a random walk actually.
Yes. So then these probability values, I mean these values, half and half or some other value, will depend on the degree of the vertex.
Exactly.
Yes.
So it is uniformly at random on the degrees. We are not assuming any kind of like distribution on the edges. No, we are not saying that B has a higher chance of going than C. So it's a uniform distribution on the degrees, over the degrees.
Like say, if I start with 1 kg of rice starting from the node A, then I will distribute 500 grams to the B and 500
That's
grams
right.
to the C.
That's
Yeah,
right.
that kind of distribution.
Yes. Nice. And oh yeah, okay. I'll just go over quickly. Okay, Satinder. Hi, Satinder. Can you hear me?
Yes, sir. Yes.
Oh, okay. So what we are doing is we are looking at Google's page ranking algorithm. Okay, or supposedly it's set to use it. I think it'll use a more complex version of the algorithm. But the crux is this: how we can use linear algebra to rank the algorithm. So you have given that page A links to B and C, page B links to C, and page C links to A. Now you need to figure out when you give them the search results, then in what order do you need to display it. Okay, and so this I can make a graph out of it in the certain sense that okay, there is B is 1 click away from A, C is 1 click away from A, and C is 1 click away from B, and so on. And we construct this link matrix that we are calling, which is equal to 1 if and only if Lij is equal to 1 if and only if page J links to page I. For example, A is linked to 1 and B and C. B is linked to C and C is linked to 1 and so on. Okay. Now what we are set to do is we are set to create a stochastic matrix out of it, which means all the column stochastic, which means all the columns sum to 1. So here you have we have divided by the number of edges away from A. For example, A is connected to 2 people, so you divide these ones by 2. So what it represents is nothing but the probability that when you are in A, what is the probability that you'll get to B? Half. What is the probability that you'll get to C? Half. And from B, since there is only one node connected, which is C, one page connected, so probability that you get from B to C is 100%. Now, this is your rank vector, which represents like what is the importance, relative importance of the pages. For example, A has 23% importance, B has 50% importance, and C has 27%. If we have computed the correct rank vector, okay, then I can list them accordingly. For example, given this configuration, I can say that B has the highest importance, C has the lower importance, and A has least importance. Okay. Now the thing is, I'll multiply this rank vector. Okay, in the beginning I'm saying I'm choosing 1 by 3, 1 by 3. I'll multiply this rank vector by R, okay, which is 1 by 3, 1 by 3, 1 by 3, and I get new probabilities, okay, of moving. This is like moving to A in 2 steps, B in 2 steps, C in 2. What is the probability? And similarly, I take the new rank vector and multiply by R again, and saying that what is the probability that it moves to A in 3 steps, B in 3 steps, C in 3 steps, and so on. So what I want to achieve is, after a point, I want a vector that will never change, no, and that is my final good ranking. But the issue is that it may never converge. So that's where we use eigenvectors, okay, and say that if I have such a good distribution that will never change, it is nothing but such that when I multiply it with the stochastic matrix, okay, I'll get R itself. But it is nothing but the eigenvector corresponding to 1, no? And that is what we computed at the end. And this gives the page rank. Okay, so is that clear?
Yes.
Okay, good.
Got it, sir.
Thanks. Okay.
Sir, I have one more doubt.
Yeah.
So this eigenvector is corresponding to eigenvalue 1.
Yeah.
So obviously it has other eigenvalues as well. Let's say it has other eigenvalues as 5 and 7. Let's consider. So for that 5 eigenvalue, it will have an eigenvector, let's say px. Let's say it is x. So px will be 5x.
Yeah.
And for this particular eigenvalue decomposition, 157, it is diagonalizable also. So when we'll find p to the power n and we'll multiply with x, So the pattern will remain same only in that case also. So is it always the case that we need to start with eigenvalue 1, or if it is diagonalizable we can play with other eigenvalues as well?
Oh, you okay. So you meant if you choose another eigenvalue, which is uh,
Right,
not you don't mean a scaling of the original eigenvalue. You mean a separate eigenvalue altogether.
right, yeah.
Um, See, the issue is that that time you're not assuming a stationary distribution, because what you are saying that is like P times R is 5 times R. This is not a
Right.
stationary distribution, no? So you are increasing the probabilities. And
At the end of the day, we are going to normalize them also. So to
you
make
are
them
going to
a
normalize them,
unit
but what?
eigenvector.
Yeah, but you will get an R that will increase by one step. Maybe after the on doing that new step 5R, and then you apply P, maybe it goes down again probability.
It will go to 5 square r, no? In that similar way.
No. Then what you are
5 square,
assuming
5
is
cube.
P times now no. Now you don't have a control over what happens now. Oh, you mean that since it's an
I'm
eigenvalue.
saying that r is the, yeah, right. R is the eigenvector for
So
eigenvalue 5.
okay. So what you are saying is now you'll go 5R, right? Oh, sorry, I mean 5PR.
Right. Mhm.
5PR. Oh, okay. Yeah, then you'll converge to the main R. Let's call it R hat, and then you'll do 5 times PR. Okay, yeah, that's good observation. Then it means that in 2 steps you can get to um, um, but ultimately you are doing this, right? But what you mean to say is at the end I'll divide by 5.
No, at the end we are going to you make it unit eigenvector by dividing by the with the that L2 norm.
So see, when you do this you get 5 R hat, no, where R hat is this eigenvector, okay,
Uh, okay,
and you
why?
need to divide by 5.
No, sir. Actually, I think I'm not getting this step. So 5 is the eigenvalue, r is the eigenvector corresponding to 5, right?
No, that's not what I'm saying. So what you are saying, so what, okay, see,
I'm saying that,
you did
yeah,
PR equals 5R. No,
yeah, right.
now I want a guarantee to reach at the stationary distribution. But what I'm saying is that when you multiply uh, with this new value, okay, let me call it R prime. So you do R
Right.
prime times P, which is nothing but P times 5 times R, which is nothing but
It
5
will
times
be 5
PR,
square, yeah, and it will be 5 square r.
which will be 5 square R. Yeah, which will be 5 square R.
So if we do it for long enough, we'll definitely scale each of the factors. Like we'll
Definitely.
scale each of the components. But isn't the scaling happening to everyone? Like isn't all the components are increasing in some particular sense?
Ah,
That when we do the
yeah, because see, internally you are computing the eigenvalue. You are computing the vector corresponding to eigenvalue 1 internally, because
right, right.
you are not stopping here. No, this particular R,
No.
okay, may be different. This is the eigenvector corresponding to 5. But now what
Mhm.
you are doing, you are applying P again, and then getting an R which is converging to this. You get what I mean?
Yeah, right. But why are you saying it will converge to this? I am not able to see this particular
Ah,
thing. That
so
why
so
it will
so what
converge
I'm saying
to.
is now you'll do P. What I'm saying is okay, let me clean this up. So you do this, okay, you get this. Now I'm saying you need to stop. I not you need to stop, but you need a guarantee that this is the best ranking that you have, and after this your uh, probabilities won't change. But I'm just saying that okay, what if it happens that okay, and I'm calling this guy R prime. I'm saying I do P R prime, okay, because I'm checking whether the probability is going to change or not. When I do this, then maybe the eigenvector will go down or increase, but I want it to stop. the analysis says that PR prime is nothing but 5 times, right, PR.
Okay. Right. Right. Yeah.
Okay, 5 times PR. Now, oh, okay, I get what you mean. So you mean to say that this, the R that I'll finally compute will be the eigenvector corresponding to 5, to 5.
Right. Right. So if I start with that, so
Hmm.
we were starting with eigenvector corresponding to eigenvalue 1.
Hmm.
So suppose let's say R is 1 2. Can you write that R equal to 1 2 for a 2 by 2 matrix? In a black right, 1
1,
2,
2.
and the eigenvalue, let's say eigenvalue is 5
That's right.
corresponding to this. So the first time I'm computing R1, or let's say R2,
Yeah,
it will be 5 into 1 2.
yeah,
But again I'm normalizing it, so
yeah.
to get a unit eigenvector. And
Yes.
after that I'm doing R3, which will be 5 square times 1 2, but again I'm normalizing it. So my doubt is, after normalizing it, isn't
Got
it
it now.
converging, or isn't it becoming the same thing?
Got it now. It's so. What I'm trying to tell you is that even though this is R, okay, and 5 times PR, and this is R. Wait, not R. R prime. No, you get 5 times R prime, and then you'll do it again, and you'll get square, and you'll normalize it, and so on. But you are increasing by 5 each time. No,
Right, we are.
you are not guaranteeing a stop to this process. You are increasing the probabilities like anything. You have chosen such a rank R that will keep increasing if you keep doing this process. You
Okay,
want this
but
process.
how will it keep increasing if we normalize it afterwards? So let's say
Okay,
R2 will be 5 into 1 2.
yeah.
So
Okay,
let's say
but
this is
see,
R1 that we started with.
I get what you mean. You say if you normalize it and then I'll multiply with 5, it'll keep, and it'll increase again, I'll normalize, and so on, right?
Right, exactly.
But that's not what I mean by increasing. I'm meaning, look at the process just before you normalize it.
Okay,
Okay, look at the process just before you normalize it. It becomes PR equals 5R. You have increased the probabilities at this point. Now, let's say you decide to normalize this.
right, yeah.
Okay, now you decide to normalize this. I agree that now all the values will go down. Okay, all the values will go down in a sense that it may be reduced by. Will it be reduced further? The on doing. Look at the normalized version of R. Okay, this R, and look at the resulting R. Look at the resulting normalized 5R.
Right.
Okay, look at the resulting normalized 5R. Let me call it R prime cap. What is the relationship between R hat and R prime? Their normalization will be arbitrary, right? But if you choose the normalization that you were saying, divide by 5, then they will be same. I agree.
I have a point here.
Yeah, go ahead.
Okay.
So even if we follow the process, Rohan's process, but for the large values of n, we would be computing the value of 5 raised to the power n, and which is huge.
Right. But
yes, but
when you divide it by that 5 to the power n into 1 plus 2, convert into probability.
So if you divide it by 5, then again and again you would be computing the eigenvalues, number one. And if you do not divide it by, if you do not normalize it, then eventually you will end up with the calculation 5 raised to the power n. And for the large values of n, computing this 5 raised to the power n would be a difficult task. And in this original form, what is happening that you need not to compute the eigenvalues or eigenvectors again and again. You have to compute it just once, and then you are pretty sure that how many times, I mean, irrespective of how many times you repeat the process, this is going to remain the same.
No, why do you need to find the eigenvalue in the next time? The P original matrix is same, no? So
P is same,
finding a new,
but then at the time of normalizing it, you would be dividing all the values by something, isn't it?
but it is for the rank. So I'm keeping the P matrix intact. So once I have found the eigenvalue,
So
Okay. So
just
you will keep
okay, right, right.
yeah.
Right, I got you. So you're saying that it will not be eigenvector to that particular value anymore after normalization, right?
Yes.
yeah,
Okay,
that is
okay.
a good point. Um, that yes, you'll increase the steps of computation,
Hmm.
and
Uh,
additionally,
but won't it be? Sorry. Go on, sir. Yeah.
additionally, um, yeah, just one moment. What is I thinking? Oh yeah. So thing is, if you get an r hat and you want to multiply it with p again, okay, you get an
Right.
r hat and you want to multiply with p again. Then, in order to preserve our process, r needs to be a stochastic matrix. In order to r to be a stochastic matrix, the only way is that I do an L2 norm.
When you're saying R need to be a stochastic matrix, that are you trying to
All
mean that the column sum will be one?
column sum should be one.
So R is a single vector, right? So all the sum of the elements will be one. That you mean?
Yeah. So
Okay. So, but okay. Yeah.
okay, now
Right.
now
Go on,
now
sir.
now I'm saying you have done you have looking at the L2 norm of r hat, and you are looking at the L2 norm of 5r. Okay.
Right.
Sorry, L2 norm of 5, not r hat. So r is the thing you started with. Okay. L2 norm of this and L2 norm of this. Okay. This will change
Yeah.
arbitrarily. This will change arbitrarily.
Okay.
You get what I mean? I can no more say,
Yeah.
okay, the probabilities will change arbitrarily.
Okay. Okay, sir. Yeah. I will do that with one example, exactly calculating that. Then
Sure.
I'll have the better picture
Sure.
that it is happening.
Sure. So that's what I meant
Okay.
by the probabilities will increase. It'll increase already before normalizing it, and after you normalize, it'll still remain increased.
Right.
Okay,
Yeah.
because I agree that if the way that you are finding the norm here, you are normalizing it here by just multiplying by 2. I agree that
Right.
if this is how you normalize it, probabilities will not increase because you can just divide by 5.
Right.
But if you want to continue this process and do a check whether I multiply with p and r hat, whether the distribution will converge or not, I need to normalize it into a stochastic vector. No,
Okay.
okay, and
Uh,
if I
right.
need to do that, then I need to find the L2 norm.
Okay, but after dividing 212 by 5, isn't it also a stochastic vector? Like, can't we say that 2 by 5, 1 by 5, and 2 by 5 without taking the L2 norm, just dividing it by the total sum? Isn't
No,
it also a stochastic vector?
no, because you will get an R which is oh, okay. So you want to normalize it in this sense that uh, okay. So what you mean to do is that as long as I eliminate the 5, the R will remain stochastic.
Right.
So if R will remain stochastic, uh, then I can normalize it back again. I can normalize it back again. Oh, okay. Oh yeah, okay. Please continue. I shall be back in 10 minutes max. Oh, okay. I forgot. Sorry, you had asked for a break. No, go ahead. Okay. Um,
No
sure,
issues. Please continue. I'll be back in 10 minutes. No issues. Please continue.
sure. Okay.
So,
So
in this break, can we just take one particular example? I'm getting your point actually. I just want to see with one example actually. So,
sure.
let's say this vector 1, 2 for a
Yes.
square matrix. We are not naming P. So, P is the matrix
Hmm.
in a blank page. Yeah.
So we can do with this itself maybe.
This one is a lot
Oh,
bigger
okay.
actually,
You
3
need to
by
find
3.
the
So I'm trying to
eigenvalues.
take a 2 by 2 example. Yeah,
Okay,
yeah.
okay, okay,
So
okay.
let's take the eigenvector is 1, 2 corresponding to eigenvalue 5.
Yeah. One
Yeah,
moment.
this particular case. Okay. And
Okay.
let's not go into P. So let's say that there exists a P for which there is an eigenvector this and eigenvalue is this.
Mhm.
So and now I'm saying that let's calculate R2 considering this as R1. So R2 will be PR1, right?
That's right.
Yeah. So it will be 5 times 1, 2.
So what you already had was that on doing PR1, I get 5 R2, right?
Right. Not exactly 5 R1 it will be. So it is eigenvector.
Oh yeah, sorry. Yeah, 5
Yeah.
R1
And PR1 is R2.
5 R1 is R2.
Right, right. So R2 will be 5 times 1, 2.
R2 will be
5
5
times
times 1 2. That's right.
1, 2 column vector. Yeah. And let's give a arrow to write the to write the norm of it after normalization. Not L to norm, just dividing it by that
Sure, sure,
particular thing.
sure, sure.
Yeah. So it will be dividing it by 5 times 1 plus 2.
You mean dividing by 1 by 5, no? By 5, no?
Dividing it by the column sum. So total column sum will divide it. So
Oh, you want to normalize the vector entirely. Okay.
right, right.
Okay, let me call
So
it
it's
half.
divided by total column sum.
So 1 by 3, 2
So
by
column
3.
sum will be right, right, exactly.
Okay.
Now let's compute R3.
Hmm.
So can we appreciate that R2 is still an eigenvector corresponding to eigenvalue lambda equal to 5? It is, right?
Let's check that if I want. So this
It will be
is
because 1, 2 is still there and remaining are the constant.
1, 2. But what is R2? R2 is this. Yeah.
So that 5 won't be there because I'm dividing by the column sum. So 5 will go inside and it will be 5, 10 and we'll divide it by actually 15. So it will be 1/3 and 2/3 in R2 hat or R2
You're
cap.
dividing by the column. Okay, column sum along with the scalar. That's what you're saying.
Right, right. It will go inside and yeah.
Sure, sure. You
So
mean
it will
it
be
will be
1/3 and 2/3.
5 and 10,
10.
and
Right, right.
here you mean 15. So
After
one
yeah.
third and two
And
third.
2/3. Yeah, right.
Hmm.
And
Okay.
now while calculating R3, we'll find P R2 hat. Let's say R3 is equal to P times R2 hat.
Right.
Right. So it will be, so we can bring 1/3 outside. So it will be P
Sure.
into 1/3 times 1, 2. Yeah.
Okay.
And P12 is again 5 times 1, 2.
P12 is again 5 times 1 2. That's right.
So whatever is outside, it is the scalar. It will get cancelled after the doing the capping thing, after doing the normalizing part.
Hmm.
Whatever is outside, it will get cancelled out while dividing it by the denominator. Again, we'll do R3 cap. So if I find R3 cap,
See, but uh,
my point is
okay, okay.
R3 cap will
Continue.
be R2 cap.
R3 cap will be
Yeah.
so this
1/3
will get to
and 2/3.
5 third. Oh no, wait. Straight to
Yeah, right, right. It is
third,
5/3 and
10 third. Okay.
so again I will divide it by the total column sum,
Hmm.
and it will give you 1/3 and half.
1/3 and half.
Yeah, column sum is here. The column sum is 5, right?
Yes. That's right.
So again and again, I'm seeing that I'm coming to a stationary point, 1/3 and half.
Mm-hmm.
So why can't we go by this? So that's what I was asking essentially.
Okay. No, that's a good point. So What you are saying is I can pick any eigenvalue and you will reach the stationary distribution using the eigenvalue. The eigenvector will be the stationary distribution.
Excuse me, sir.
Yeah, Sanjay.
Uh, just I'm asking what the eigen values we are taking. It is corresponding to P matrix. Just it is a
Ah.
arbitrary choice.
So what?
Yeah,
Not
P
not
matrices.
not the previous P matrix, but this is a bottom. I mean, we are thinking it in terms of bottom up in a sense that consider a P such that the eigenvalue is 5 and eigenvector is 1.
So far, what we have studied, that is ax equal to lambda x.
Yeah.
That corresponds to only on the A matrix itself, no? Because values will come corresponding to the A matrix. So here, what we have taken the P matrix, so that lambda is not satisfying. So it is not like we are taking any arbitrary values.
Oh, yeah. So no. So we are just taking an example. No, I think you will be able to construct such a P that for which this is the case. But I think this observation is independent of what you choose. It looks like that. It's not because you've chosen 5 and 1/2 that we are getting this. If you take a proper P and a proper value and eigenvector, you should still be able to see something like this, because so far there is nothing that
Yeah, right.
nothing
So
that
for
looks like it
lambda,
is coming from the choice of 5 and 1/2.
What
Because
we
if you
have
chose,
taken.
let's say, 5 to something like 10 and 1/2 to something like 2 and 1 to something like 2 and 3, this operations will still be similar. So what?
Actually,
Yeah.
my, my doubt is ki, like what P matrix we have taken. No? The first question we have solved.
Huh.
Uh,
So in the first question, I was insisting that
lambda
you
equal to 1 you have taken. So
yes.
actually, I was constructing the eigenvalues. No, a characteristic matrix I was
Huh.
forming. So it was lambda was not coming as 1. So there I got doubt little bit.
no,
Like
it will
how,
come as one because column sum is one, no? So it has to come one. So there might be some mistake, but the column sum is one.
Yeah.
That means the eigenvalue has to be one.
One will feature as an eigenvalue here.
And you can cross check also. Like you can multiply that by 212 vector, and you'll see that you are ending up with 212. So that means one is an eigenvalue.
is it coming 1? Can you check? Like
So
Yeah.
what were the other two eigenvalues you got, Satinder?
no, I've got the characteristic equation. Maybe minus lambda cube plus lambda plus 1.
No, okay.
This I've got. So here 1 is not satisfying that one. No? So,
Oh, okay. Oh, that should
because
be, yeah, okay. You should cross check that once, because you should be getting,
okay,
okay. Yeah.
okay.
Okay.
I'll check it again.
Sure. Yeah. Okay, Rohan. I don't see an issue with this actually. Right now, it seems like you can actually take an arbitrary. Oh, but wait. Okay, the question is, wait, is it convergence R3? Oh, okay, yeah. So what you meant to say was, um, you got 5 1/2, and you got 5/3 1/2. Ah, okay. Internally, that is what is happening. So the way I see it,
Sir,
Rohan.
okay. Can we check the
Yes, sir, yeah.
P matrix was 0 1 1
Yeah, no, 0 0 0 1.
0 0 1 P for column wise.
Oh, okay, 0 half half.
Okay, 0 half. Now, yeah, done half one. No? Then it will come. I've
Yeah.
taken 0 1 1. I've
Oh,
taken the
okay.
initial.
Oh yeah,
That's why
that
we
was
have.
that link matrix. Yeah.
Okay,
Okay.
got it.
Yeah.
Got
Okay.
it.
Good.
Sir,
Huh.
uh,
Yes. What would we
uh,
saying?
for
Oh
that
yeah.
particular
Yeah.
matrix,
So now,
so you
yeah,
are saying
I'm
something.
not. Yeah, I think yeah, I was almost convinced. Now I'm not because
Okay.
whether 5 is the eigenvalue for this vector or not, that is actually um, see what I mean to say is, what if your eigenvector was 1 2
Right.
x1
Right.
and
So,
you chose your x1 to be 5?
so are you saying that eigenvalue is x1, or what are you saying about x1?
No, that's what I'm saying. So uh, what if you what if one of the variables was not free and you chose x1 to be 5,
Which
and
variable is not free?
so there is x1 x2,
Right. Right.
and you got that x2 is equal to 2x1,
Right. Yeah.
and you got okay, no, what I mean to say is, I think to perform a proper analysis we need the value of p somehow, because um, so what I simply mean is that, let's say this is what you have
Hmm.
as your eigen vector computation,
Right. Right.
and x1 you chose as 5.
Okay. Cool. So the eigenvector that we are playing with is actually 510, right?
Yes,
It's a
510.
column. Yeah. But still the eigenvalue is 5, right? Or what is the eigenvalue that we are considering? Let's say it is lambda. We can
That's
keep it
right.
a general one actually. So so in that case also PR1 will be lambda into 510.
Lambda into 510, that's right.
But after doing the same normalization, it's not normalization.
It's
I'm
not
just dividing it by
normalization,
the column
exactly.
sum.
But now you
Yeah,
have
right.
lambda equals 1, right?
No, but it will still happen, right? Can you just write it somewhere? Because I
Yeah,
was doing
so
it with
what I'm
the
saying
general
is,
thing,
so you have PR1 equals
right?
510. Oh, P510.
And in front of it, we have a lambda, right? In front of it, we have a lambda,
You have a lambda, that's right.
right?
Now,
And
lambda,
can
you'll
we
choose a
name it R2?
scalar, okay,
Yeah, just name it R2, and then we find R2 hat.
yeah.
Yeah, R2 hat will be this whole thing. So 5 lambda, 10 lambda, this matrix divided by the column sum.
Hmm.
So the column sum is lambda 15 lambda, right?
Yeah,
So after dividing it by the 15 lambda, it
you'll
will
get
be
1 2
again
back.
half and one third. Yeah, one third and half.
Okay, okay. This is a good point. So far, I don't see anything too strong against this. So it
But
may be
actually,
the,
sir, I know that this is the wrong approach. So actually, I know, I know, not for sure, but I know that one like eigenvalue one will help us. I'm just trying to play a contradiction because you are there, so we can with me only. I cannot play the contradiction game. So I will just
yes,
try to like create a problem there, and I will see why it is not acceptable. So till now, if we have eigenvector corresponding to one,
huh,
that is a different eigenvector.
hmm,
So which of these two rank vector will we accept and why? So eigenvector corresponding to 1 will be different compared to eigenvector corresponding to 5.
huh.
The eigenvectors are different itself, no matter after doing the normalization or whatever.
Yes.
But which eigenvector we should accept as the rank vector and why?
That's yeah. Well,
So since this is a probability matrix, so the largest eigenvalue possible would be 1. All other eigenvalues would be less than 1. So eigenvalue cannot be 5, one thing. It could be anything else, but cannot be 5 at least. It could be
Oh,
1 by
you
5.
mean since it's a probability matrix, its lambda
Yes.
cannot be.
Yes. So
Oh,
the value of eigenvalue, yeah.
oh, that's an
So
interesting point.
yeah,
Okay. So, it's you checked up this fact on the internet.
How are you so sure? Like, is it a very standard result that the stochastic matrix have eigenvalues less than equal to 1?
Let's check
yes,
that out.
yes. If for the Markov thing, the largest eigenvalue is a 1. That I remember. I don't. You can check it out on the net for the Markov thing. The largest
So,
eigenvalue is 1. Yes.
Okay.
he is probability matrix. So let's say, hmm. So let's say this was A B C D, and this is x1 x2. Determinant lambda p c t minus lambda. Oh, it's a standard fact. So okay. No, I was just trying to think on why it should be, but okay. That's a good point. Good exercise.
Okay. So even if it is,
So
so
if
let's consider the eigenvalue is 1/3 or half.
huh,
So yes, go ahead, sir. Please continue.
no, go on.
Yeah. So if the eigenvalue is half or 1/3, what is the problem then? Why the corresponding
So
eigenvector we can't choose?
if the values are in fraction, so
Right.
then if you increase the value of, if you keep on increasing this, earlier you were saying 5 raised to the power n kind of the thing.
Right.
So
Right.
now the things will become like 1 by 5 raised to the power n thing.
Right.
And
Right.
if the value of n becomes pretty large, so then its
Yeah.
contribution effectively will get diminished. And so therefore probably 1 would be the most appropriate thing.
But we can
So even
like.
even if you consider, say, all eigenvalues, then what will you say? That okay, in this direction we do observe the maximum variation, but then as you increase the value of n, the variation in that direction will get diminished, and the maximum variation would be observed only in the direction wherein the value of lambda is a 1. Isn't
Okay.
it?
And why are we interested with the maximum variation thing?
Obviously,
Why
clearly,
so?
because then we want to rank the vectors, and we want to
Yeah.
rank the vectors in such a way so that we are interested in knowing that which node is contributing the most. So
Right.
the variation of the node A would be largest in a direction, and that direction will not correspond to the fractional value of the fractional eigenvalue. Because as you increase the value of n and you keep on repeating this stuff, so then the contribution in the direction will become almost zero after, for a pretty large value of n, that kind of thing. This is just an argument, and you may find the better things.
No, it's a good idea actually. So okay, in that direction.
So like
Contribution.
like in the PC, like in the PCA also, we usually take, say,
Right.
first two. Why so? Because in those directions only we do observe the maximum variations.
Yeah, but in PC, our target was to see like data compression, which are the components are like essential, which we can take and discard others. Still, it will
So
like keep all the pictures safe.
yes,
Right.
and how do we reduce the dimension then? We reduce the dimension on the basis of identifying those variables which do exhibit maximum variations, because then
Right.
those
Right.
variables would be fruitful to us, right? And
Right.
if we go by that logic, then we would be interested in moving in the direction wherein the node B exhibits a maximum variation or is having the maximum impact, and that will correspond to the value of lambda is equal to 1.
Okay. Nice. But what if I say that after doing R2 and R3, if you are finding the R2 hat and R3 hat, they are coming to a static position and which are not diminishing. So what will be your argument then?
So then it would be okay, but then this really happen? Say if you consider the value 1/5, so 1/5 r and then 1/5 square r. So this will get diminished only when n approaches to infinite.
No, so in between you are not doing the normalization kind of a thing. So I'm saying that in between, if even if you do normalization, that will still remain eigenvector, and it is
So
remaining.
I do not understand the meaning of normalization here, but I think that if you change values in the matrix P, probably you will have to compute all the eigenvalues from scratch. The
Not really,
eigenvalues
actually.
won't be the same. Okay.
So okay. Let me bring my point. So let's say 1 2 is still the eigenvector, but now lambda is not 5. Let's say lambda is 1 5, and for that particular thing, let's keep it lambda only, and the condition is lambda is less than equal to 1. Okay.
Yes.
Or let's say sir has written epsilon here, so let's take it epsilon only, and the eigenvector let's write it as 1 2. So my argument is it will converge to 1/3 and 2/3 always.
1/3 and 2/3 converge. Okay, maybe yeah, but converge. I mean, I do not understand whether it will really converge or not. But go for the basic equation that r is equal to pr, say, and
Okay, r equal to PR means,
pr is equal to lambda r, right?
Right,
and now
right.
you put
Let's
the
say
value
PR.
of lambda is equal to 1/5.
So we don't need to put exactly the value. We can have the consideration that lambda is less than equal to 1 for the general case.
Yes.
So all the cases are tackled. Yeah. So and let's name it R2. So R2 will be lambda r, right?
Yes.
See,
And can you write R itself? Yeah.
yeah,
Go
yeah.
on, sir.
So, okay. So, the two things. Okay, first thing is that we would want to move to the next question also. Okay, so
Okay.
we don't want to. I would say let's not spend too much time on this. But the next thing is that I think I'm convinced now, Rohan, that
Yeah.
if your method will work if the technique of normalization that you use is, like you said, dividing by the sum, and I'm convinced that this will not work. It won't converge if you use the L2 norm. Now that I'm thinking about
Right.
it, okay.
Right.
So
L2 norm it will not converge.
yes, so it will depend on the type of normalization you do. If you use the type of normalization you are suggesting, then it will not. It will converge. Definitely, it will converge because you are actually just removing the factors. And
Yeah. Right.
but what that will lead to is like multiple eigenvectors, and which means that you have multiple possibilities for the distributions. So
Right.
I am not sure if you have multiple possible distributions, then which one you will use to rank. That is,
Yeah.
and that would mean that we'll need to do a deeper study into, what would be a better, fair kind of process. There is this a field of study called fairness, where they study these kind of things. That it may not be that the one corresponding to one eigenvalue one is the best. Maybe because now we are considering different eigenvalues, maybe there are other better things. But we'll need to choose a particular parameter and then study that process. But yeah, that's what I think. Okay.
Okay, sir. Yeah, that makes sense. Yeah.
Okay. Good. Okay, Goel, is that right? Hi, Goel.
Yes. It is
Okay.
fine. Yeah.
Okay.
Please
Okay.
go to the
Let's
next
move
question.
on to the next question. Okay. uh, okay. So have you guys seen codes? Anything from coding theory, error correcting codes?
Yes, sir.
Yes.
Oh, good. So what kind of codes have you seen?
So, like say every code is a triple NKD. N is the number of the bits in which we are transmitting the data, and K is the size of the message, and D is the minimum distance.
That's
And
right.
for the different codes, I mean, we just have to manage without increasing the value of N, we want to increase the value of D so that we should be able to correct more number of the N's.
That's right. Yeah, yeah. But okay, Rohan.
I only know Hamming code, sir, and
Oh,
rest
okay.
of the things I don't know in general.
Oh, okay, good. So we'll look at a generalization of codes, generalization of Hamming codes also. Okay, these are called linear codes. Okay, it's used all over the place.
Okay, sir.
Okay, so linear codes. Why is it called linear? Well, there is linear algebra involved, and more specifically, there is a linear transformation involved. So, I mean, in this question, we'll see like why Hamming codes work. Okay, or why
So
any
linear
code
could be
works. Yeah.
so linear could be because of another reason also. Say if we take two code words, and if I take their combination, linear combination, that will result into another code.
Exactly. Yeah, that's right. They are linear with each other. That's right. So here, so the idea of code words is, let's take the same example. So encodes 3 message bits, 5 bits, 5-bit code words. Okay. So the idea is that I need to send. You have Alice, you have Bob. Okay, and Alice has a 3-bit message. Okay, let me call it X. Okay, she has a 3-bit message that she needs to send to Bob. Okay, now the issue is that the channel that is there is noisy. Okay, so what it can do is, if Alice is sending, let's say X equals, Alice is sending, let's say X equals 0, 1, 0, then on sending through the channel, Bob may receive this 0, 1, 0, where this last 0 gets corrupted, then Bob may receive 0, 1, 1. No, that is an issue. So how does Bob detect it? How does Bob correct it? So then you have something called error correcting codes, and more specifically here we want to look at what are called linear codes. But the general idea with coding is always that Alice will try to inflate, blow up, artificially blow up, inflate the input so that Bob can actually figure it out. For example, a simple artificially inflate would be that she'll just double the message 0, 1, 0, 0, 1, 0, and Bob will receive 0, 1, 0, 0, 1. And let's say this again, the last bit got corrupted, then Bob will receive 0, 1, 1. Okay. Now what has happened? Bob noticed that, oh, okay, the first 3 bits are 0, 1, 0, and the last 3 bits are 0, 1. So Bob knows now that there is an error. But can he correct it?
Yes, by adding some parity bits here. I mean, and then later on checking that whether this.
Yeah, exactly. Yeah, but in this situation, can he correct it?
So I can do some kind of, like, say, checking that like here I have 3 ones here in the receiving thing, and then even parity or odd parity kind of the thing I follow. I could not understand the question precisely, but
So
probably you have
Alice's strategy is she'll just double the message and send it over.
Oh, I see.
Okay.
Double the message, right? Yeah.
Duplicate.
So like in this case, yes. So I mean, doubling the message, say 0 should have been doubled here, and but then we are getting a 1 instead. So therefore, this last bit got flipped.
Yes. So now Bob will be confused on, okay, there is an error, but I don't know whether the error is in the first block or the second block, and which bit in those blocks. But he knows that there is an error because the first half is not a copy of the second half. So all Bob can do is detect the error. No, but he cannot correct. So
at this point, the Bob Yeah, can take the XOR of both the halves.
Yes, but Alice has not communicated. No, even if Bob does XOR of both the halves, what will he get? He'll
So
just
he will get something non-zero,
he'll,
and wherever he get non-zero, I mean, I could not understand the question, but then probably you mean to say that every block is getting transmitted twice from the Alice side.
yes.
Uh,
So
and
this is all that Alice has sent. So
yes,
this is all that Bob has received. There is no way
yes.
to detect, no, in this
No,
case.
now the Bob will take the XOR of both the halves,
Okay,
and the Bob will get the last value as 1, indicating that the bit has got flipped
this is
at
one, this is
the
zero.
yeah.
That's what you mean?
No,
Okay.
not this one. 0 1 0 and then 0 1 1. Take the XOR of this thing. 2 blocks.
Yeah. So 0 1 0's XOR is 1 and 0 1 1 is 0. He knows that. No,
Yeah.
I'm saying he can detect it. I'm saying correcting.
I could not understand. So he can detect, but what did he
But I'm
say?
saying, can he correct? That's what I'm asking.
Yes, he can correct. And based on the position of I mean, the XOR result, in the case of the XOR, the first two bits would be equals to two zeros and followed by a 1, and indicating that an error has occurred at the last bit. Because wherever there is a difference, the XOR value will came out to be a 1 if the values are not same.
No, I don't understand how you are doing it. So,
So take the XOR of 0 1 0 and then 0 1 1.
yes, you get 1 and
And
0.
no, the result would be 0 0 and then 1.
Why so?
You take the XOR of this thing 0 1 0 and then 0 1 1. The first three bits as 0 1 0,
So you
and
are
the
doing,
second.
yeah, that's what you are doing. 0 XOR 0 XOR 0.
No, not
So
like
0
this.
XOR 1 XOR 0.
Yeah,
No.
yeah, 0 1 0 and then 0 1 0 1 1.
Oh,
You
okay, I
can
get it.
write 0
You're
1
doing
0.
bitwise XOR. Okay.
Yes, bitwise XOR, right.
0 1 0.
0 and 0 1 1.
Yes.
Take the bitwise XOR, and then you will get this result as 0 0 and then 1.
Yes.
So wherever the Bob gets a 1, this is an indication that the bit has get flipped here.
Bit has gotten flipped at the last bit. No, either here
Yes.
or here. Yeah, that he can do by comparing one by one, or he can do an XOR like you said. That's fine. But now what I'm actually saying is, for correcting, you need to know whether the first half was a 1 and this got flipped to a 0, or the second half was actually a 0 and it got flipped to a 1. That you cannot tell, no?
So no, yes, this can be detected. This can be corrected. Why so? Because then the Bob would be knowing the first three bits, and he knows that
But how does
he
Bob?
knows the.
Yeah.
But then Bob knows the policy. Bob knows the code being used. Like in this
Yeah.
case, the Bob knows that yes, the repeated codes are being used, and every block is going to be the size of the block is 3, and it is going to be repeated twice. And if
He
that
knows
is the case, then
he knows that it's going to be repeated twice, but he does not. He knows that okay, he can figure out even that the last bit is corrupted, but he does not know that is it 0 1 1 or is it 0 1 0. It should be one of these two, but which of these
Yeah,
two is the correct answer?
yeah, right. Yeah,
That's what
I
I'm
agree
saying.
with it.
Okay,
Yeah, true, correct.
so one possibility is to send 0 1 0 0 1 0 0 1 0. Okay, and then let's say the last bit is flipped, then Bob has two more copies, and so he can know which one was flipped. But the issue is that there. What if what if they flip 2 bits? What if the noise is going to flip 2 bits, 3 bits, some more bits? Right.
Yes, then
So,
it's possible.
like you said, we can do an additional parity check that not only will you um, um, you can. So, can you do an additional parity check that you say that oh yeah no, I mean, it'll depend on the number. You can keep increasing this. I can add parity bits, but again, it's if you increase the number of errors that are possible, then there is no point there. But that's what we want to make. We want to make a kind of codes that will be very strong against errors, and you want to generate them well. Okay, and therefore you have linear codes. Okay, they are very well, very good codes. Okay, and for example, Hamming codes is one. You cannot do better than Hamming codes. Okay, so um, so here now this is the idea of linear codes. Okay, the idea is I'll look at the bits in terms of f2, the field f2. F2 is nothing but uh, 0 1. The addition is mod 2. Okay, so in other words, plus, doing a plus is nothing but doing a parity, an XOR. Okay, now the idea of linear codes is that if I have my message of, let's say, m bits, I'll multiply it. Okay, it's the other way around. If I have my message which is of m bits, then I'll multiply it with a matrix to get my code word. Okay, so this is what n1 cross n, 1 cross m, which is the message, and this needs to be m cross n, and therefore I'll get a 1 cross n. Okay, so n is the inflated message, as you can see. Like Alice was inflating by double or triple, right? So this is the n. This is the uh, 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 message that Bob receives. Okay, and the idea is as follows. That is that think of Alice's inputs, okay, which is like 0 0 0 0 0 1 0 1 0 and so on, 1 1 1. And let's say she inflates it by 5 bits to 5 bits. Okay, 0 0 0 0 0 0 0 1 0 0 1 0 and so on, 1. Is it 5 bits? No. Now it's 5 bits. Okay, now on multiplying with the matrix, let's say on multiplying with the matrix, 0 0 goes to all 0, and 0 0 1 goes to this guy, 0 1 0 goes to this guy, and let's say 1 1 1 goes to this guy, and this is how it's getting mapped. So what is the size of this set? This set is of size 2 to the m, and this set is of size what? 2 to the n. So since every value is getting uniquely mapped to 1 because of this matrix, let me call this matrix capital C. Okay, because it is getting uniquely mapped to each of these values, and this n is much greater than n. N is greater than m. Okay, it's 5 here, it's 3 here. No. So which is nothing but 2 to the m is 3, which is 8. 2 to the 5 is 32. Oh, sorry, 2 to the 8. Yeah, 2 to the 8. So there will always be values here which are not mapped to at all. Okay, so there are values that get mapped to. For example, this guy gets mapped to, this guy gets mapped to. Let's say this guy does not get mapped to. Okay, this gets mapped elsewhere. So this does not get mapped to. So these which get mapped to are called code words, and these which don't get mapped to are called non-code words. Okay, so now what is the idea? Okay, non-code words. Now the idea is as follows: that Alice chooses a set of code words, which are mapped to by the matrix. So she chooses the matrix, okay, a set of code words such that chooses a set of code words such that they are far apart. They are far apart from each other. Okay, what does it mean, far apart? So if I have a value 0, 0, 1, 0, 1, and I compare it with 1, 1, 0, 0, 0, 1, then the distance is the places where they don't agree. Okay, so 1, 2, they don't agree. Okay, so they don't agree here, they don't agree here.
So one bit is missing there. It has 5 bits in the former one.
Oh yeah, okay, sorry,
And
thank you.
let's add one more bit. Yeah.
So okay, this, let's see. Okay, and they don't agree at 3 places, so the distance is 3. So I want those code words which are very distant from each other. And what does Alice do? Alice knows that any message she writes through C, that gets multiplied with C, okay, gets mapped to these code words only. And these code words are far apart, which means that they have several places where they don't agree. Right. So that is called the distance of the. Okay, I'll come to that. They have several places where they don't agree. Now, if let's say, so something like this should not happen, like 001, 0001, they are just too close to each other. Okay, but so let's say remove this, and let's say some code is there like 011101. Okay, so this is far apart from the first code word. It is at a distance 3 from here. What that means is that if the channel or adversary corrupts any of these bits, okay, since the channel corrupts any of these bits, Bob is not confused between them, okay, because he knows that the code words are far apart. So this is how it's represented, okay, usually. So these are code words, okay, and these are everything that are within the distance of, let's say, D. Okay, let me call it, instead of delta, let me call it D. Okay, okay, and let's say, and D is the distance, is the minimum distance between any two code words. Okay, so these dots represent code words, and these these circles represents all those messages of distance less than D. Okay, minimum distance between any code words is D. They are at least D far apart. So two of these pairs cannot intersect. And there could be things here in between, inside. And there could be things here inside. But two code words, there's pairs which are called Hamming balls, they will never intersect. Okay. So now the idea is that if Alice sends a message M, it gets mapped to a code word C, which is multiplied by, because of the matrix M, and C is guaranteed to be one of the center of these balls. Okay, and if the channel makes k errors such that k is less than d, then what happens? Let's say this is y. Let's say this guy is y. Now, if the channel makes k errors such that it is less than the distance, it will the new code word, the corrupted word will always lie within the Hamming ball, right? And so Bob will not have a confusion because it lies in the Hamming ball of y. It lies in the Hamming ball of y. Bob will say definitely she meant y. You get it? I need to choose my
Oh,
matrix in
nice.
that. Yeah.
Yes, sir. Yeah, got it.
Okay. Yeah. So Bob needs to choose his matrix in that way. Okay. Furthermore, okay, and this is an interesting property of codes is that I want my matrix M. Oh, sorry, not only that. I want my set of code words. Okay, their linear combination should give me another code word. This is important. Okay, to come up with this matrix M. We'll soon see that why. But what does that simply mean? That if the set of code words are closed under linear combination, in other words, so what does that imply? That the set of code words is a
Uh, didn't get you, sir. Can you
so
repeat that question once more?
the set of code words. Okay, so these dots here,
Right.
when you add them together, okay, then when you do a linear combination, you should get another code word. Okay, you should not get a non-code word. So what does that imply about the set of code words? That's what I was asking.
That we are forming a vector space.
Exactly. They form a vector space. So,
Yeah.
so these properties is where linear algebra comes into picture. Okay. So because what you have is for every linear code you have what is called a generator matrix given here. Okay, which was the matrix I was talking about here. So let me not call it C. Let me call it G. Okay. The question is saying the question is saying G is the generator matrix. For a message M, find the corresponding code word. Okay, so all you need to do is multiply the message with the code word. So for example, here the message is 101. Okay, let me not write it as M because M is a bad. Okay, let me call it Y and Y. Yes. So Y is one. Y equals 101. Okay, good. So Y times, so 101 G times Y is nothing but, oh sorry, Y times G times G is nothing but 101 times 1000010110011. Okay, if I do this, then what will I get? This will be 10111. First row plus third row. Oh, okay, you found the combination. 101. Okay. So this is the message that Alice will send Bob. Okay.
Sir,
Yeah.
this mapping is 1-1, right?
It's 1-1.
It is not a many one mapping.
No, it's not a many one mapping. Otherwise, Bob will not be able
Yeah.
to figure out what message
Okay, okay.
Alice had
So
sent.
this kind of a generator matrix will always have a full rank.
Generator matrix will always have full rank. That is right.
Okay.
Additionally, so why should that's another question. Why should the set of code words form a vector space? What if it's not a vector space?
Uh, you mean what will happen if we don't have the linearity? Like
Yes,
if
yes.
we
What
add
will
some
happen
and
if
it
you
is
don't have
not coming up
linearity?
to be a code word?
Yeah, yeah.
Uh, okay. Let me think.
So if linearity property is not being followed, then how would we have one-to-one kind of the mapping then?
Yes, exactly. Exactly. So, or let me elaborate on the idea. The idea is that this matrix is my magical box that will pop out a unique code word given for every message. Okay. And if it so happens that linearity is not preserved by the code words, then what will happen is um, this multiplication may lead a certain combination, linear combination of 101, which will be clear when we do what is called the parity check. Okay, may lead to a non-code word, right? And if you have a non-code word, then um, if you have a non-code word, then when Alice gives you a message, then there is no guarantee of restoration.
Yes, because for every message there should be a code word.
Exactly.
So if that thing is not being preserved, then for a message, quite possible that we may get something and which is not a code word.
That's right. That's right. That's right. It'll be more clear once we do this parity check. Okay. Now, um, now's the interesting part. Okay. So, okay, this is the code word. Now, how does Bob check? What Bob can always do is he can look at each of the bits and compute the distance with the code words. Okay. And if let's say one of the bits gets corrupted, this bit gets corrupted. Okay, 10101. Okay, this gets corrupted, and Bob needs to somehow detect it. But Bob can compare it with all of his code words and say that, oh, if the errors were not too large, then definitely this became 0. So definitely it is actually the code word 10111. That's what Bob can do. Right. So now here is a nice thing. Okay, what he can do alternatively is, but instead of going through each possible code word, what he can simply do is um, do something called a parity check matrix. Okay, and so that's what the question is saying. Suppose the receiver gets R equals 10101, construct a parity check matrix H satisfying HG transpose is 0. Okay, now what we are saying is that R is, let's say, 1010. Construct a parity check matrix that satisfies HG transpose equals 0. Okay. Construct a matrix H that satisfies HG transpose equals 0. And it is saying that this, what is called the syndrome S equals H R transpose will tell whether there is an error or not. Okay, so let's construct that H. Now I want to ask you guys, okay, with all the knowledge that we newfound knowledge of linear algebra, how do you find H?
Null space of this
Good.
transpose.
Yes, yes, right. So H is nothing but the null space of G, right? I hope everyone's convinced.
Yes, sir. Yeah.
Yeah. So what this also means is that remember that generator matrix represents the set of code words, no? Okay, the set of code words, and represents the set of code words. It means that so any code word will be okay a linear combination. Just don't know where is the uh, where is the okay, yeah, a linear combination of these rows and the linear combination of the rows of them, right? Because what we are doing is 101 is a message. I'm deciding what elements to pick from each of the columns, which is nothing but a process of linear combination, right? So what it means is that H C transpose equals 0 for all code words, right?
This is not clear.
Okay.
Uh,
See, okay, or I'll explain it geometrically. Okay, G the or I explain it geometrically. G represents the vector space of code words, right? Any transformation that G makes on any input, G will give a set of code words,
yes.
right? And H is orthogonal to G means that the vector space associated with H is orthogonal to the vector space of G, right? So the
Yes.
vector space of H is orthogonal to the vector space of G. So now what does G contain? G contains all the code words. So G has all these code words sitting here. Now if you multiply with H, so multiply any vector in H with a vector in G, then it will return 0.
But then we are taking transpose of C, isn't it?
Yeah, transpose of C.
Oh, yes, I understood. Yeah, fine.
Okay.
It's okay. Yes.
So so yeah, so that's what you have now, right? So uh, now you want to come up with H, right? So what you can do is now you can take the rows of G, okay, and solve for the homogeneous set of equations. Okay. So what you can do is so H is nothing. Okay. Or rather I'll say H. So this is a separate observation, or rather I can say it is enough to compute the null space of G. So let's compute the null space of G. So null space of G is those values G n, let me say, that satisfies this. No, that is a null space. So what is G? 10010, 01011, 00101. Okay. Now this multiplied with something to get 0, 0, 0. Okay, and this is our dimension 3 cross 5. So which means this is will be um, 5 cross 1. No, 3 cross 5, 5 cross 1 give mm, x1, x2, and so on till x5. So we can write it in terms of an equation: x1 plus x2, 3, 4 equals 0, x 2 plus, okay, let me shift this entire thing to the other side. X2 plus x4 plus x5 equals 0, x2, 3 plus x5 equals 0. Okay. Now, by the way, remember that we are over f1, f2. Okay. So this is addition modulo 2. So what you have is you can say x1 equals the complement of x4, and or for now I can even do minus sign, that's okay. X1 equals minus x4, x2. Now minus x4 I can replace here. Okay. X2, x3 equals minus x5, and x2 equals minus x4 minus x5. Now this is nothing but now what is x3? Oh, x3 is already done, equals minus x5. Now x5, I'll put it as x5 itself, and x4 equals uh, x2 plus x5. Minus x4 minus x5. Okay, and x1 is minus x4, x2 is minus. Okay, so this I'll replace with x1. Okay. Oh, x4 I can write it as minus x1. X4 I can write it as minus x1, and x1 I can write it as x1 itself. Okay, now I have everything in terms of x1 and x5. Can I remove x5 also? I don't think so. Yeah, that will be difficult. Okay, so now we have three variables. No? Okay. So that means anything that satisfies this will satisfy my null space. So the first kind would be that I choose one. Oh, okay, so let me separate them. So I'll write them as a vector x1, x1 minus x5, minus x5, minus x1, x5. This I can write it as x1, x1, 0, x1 minus x1, x5, and plus um, 0 minus 1 minus x5.
X5 should not be there in the first column. In the last entry, it should be 0.
In the first column. Oh, x5 should not be there. Oh yeah, what I'm seeing. Okay. Yes, thank you. 0. Okay.
Yes.
Minus x5 and this 0 and minus x5. No? And I can take the minus outside for this one.
Only X5 in the no. In the last entry, it is only X5. No. Ultimately, it will come same. Like it is not minus X5 in the last entry. It is
Oh, it's
only
not
X5.
x5. Okay, okay.
Yeah. Ultimately, it will be 1 in mod 2.
No, it won't because here we've thought of minus 1 not okay, not we are not doing the AF2 minus 1 because actually you are right. No, you are correct. Minus won't matter here. That's right. Minus won't matter. I can just get rid of minuses. So this will become okay. That was a long calculation. 0 1 0 and 0 1 1 0 1. So
Yes,
what is the parity check matrix? So the parity check matrix, just to write it in 1 1 0 1 in a transpose form. 1 1 0 1 0 because we need to multiply it. Okay. So this is my parity check matrix. Now given a code word R, okay, 10101, I can multiply with its transpose. Okay, like this. So what is this is 2 plus 5 and this is 5 plus 1. So which means I'll get a 2 plus 1 vector. 2 plus
yeah, it's 1 0.
column plus 1. I'll get a 1 0.
Right.
So when I do this, okay, what does it mean? I get a 1 0. If you notice, whatever I'll multiply on the right hand side, if it is a no matter what I multiply on the right hand side, okay, if I make sure that it is a code word, since it is the null space, I'll always get 0 here. Which okay, so if I multiply a code word C with this H because it is the null space, I'll get 0. So that is enough to indicate whether there was an error or not. But you can do even something better. That is, if I multiply with a non-code word, okay, and the distance is good enough, yeah, non-code word, and I multiply it with the parity check matrix, I'll get where the error has occurred. Okay, because this encodes all the parity information that I have so far. So now if you multiply, okay, let us take apart the multiplication. Like 10101, okay, what will the multiplication look like? So it will be 1 plus 0 plus 0 plus 0 plus 0. Okay, this matrix has by property been carefully crafted so that the parity should always be preserved if it is a code word. Because if it was, if the parity is not preserved, then it cannot be a code word. Because by parity I mean even, odd, odd. Okay, if the parity is not preserved, then it cannot lead to zeros. So as soon as this happens, then I know that okay, fine, there is an error. And then I do for the next column 0 0, 0, 0. So the parity check goes through here in this case. And because the output is 1, 0, there is an error in the column labeled 1, 0, which means that if this represents position 1, this represents position 2, position 3, position 4, position 5. If it was, let's say, 0, 1, then it would mean that there is an error in position 0, position 3. Okay, but this means that there is an error in position 1, and therefore I can correct it. I can make it uh, 0, 0, 1, 0. So this is the nearest code word. And this is how you correct. Okay. I went above time. I had several other. Yeah. Well.
So the thing is that it's okay that if the G is known, then we can compute this S transpose parity. But then how do we generate this generator matrix?
Okay. Good question. Any idea?
No, like
it
seems to me. It seems to me like a 774. No, this 5-bit code words are there. This is 5,3 scheme. I have no idea.
That's a good. So you can come up with your own code in the following sense. Okay. Oh wait, sorry. Yeah, you can come up with a code in the following sense. You take your set of messages. Okay, and you take your set of code words. I mean, not the code words, but your entire what is that called? And let's just call it possible received messages. Okay, and what you can do is you can start mapping them. Okay, you can start mapping them, and you'll get your set of code words, this red set, and there will be some things here which are your non-code words. No.
Yes.
Now what you need to do is you need to make sure that this forms a vector space.
Okay.
Okay. Additionally, what you can simply do is, as long as you put the 0 vector. So okay, here's okay. So but this process will not guarantee that you are forming a vector space, right?
Yes, I can include all the zeros in the right hand side. That is okay.
Sure. That you'll put 0 to the end, but maybe on combining these two vectors, you get something outside. So it will not form a vector space anymore. That is the problem.
Right. Yes.
Okay. So what you need to do is, you need to do it in the following order. Okay. You pick, of course, 0 to the end should be put. Okay. Now you pick a string you would like to put in this a vector space. Let us call it W1. Now, when you add W1 with 0 to the end, you'll get W1 back. So far, you've created a vector space only. You'll add another string you would want there, W2. This
but
time,
then, but then after adding 0 n, after adding say any random W1, then I can do one thing, that I will add W1 with itself. And whatever value I get,
that is good point. Yeah, you need to add W1 with itself also. Good point. Then you'll get some other thing, W3. Then you need to consider adding W1 with itself 3 times and so on also. Okay, but 3 times is nothing but W1 plus W3, right? And then you'll get another vector. And you need to keep increasing this set size until you get a vector space. That is, they are closed. You get nothing outside. Okay. Now all you need to do is get the basis vectors and write the basis vectors row wise. And this will form your generator matrix. Because now you know that any linear combination I can pick, I will always get a unique value.
And how to get the basis vector out of this space?
Basis vectors we've seen, no? I mean, you can do a Gaussian elimination and get from the row echelon form. if you want them to be orthogonal, then you can do Graham-Schmidt process to get orthonormal vectors, so on. But you need to make sure
Yes.
you are doing everything over F2, not over reals.
Yes. Yes.
Okay, so this is how you can come up with your own code.
And in the 7,4 Hamming code scheme, they have a very standard format of the generator matrix.
Yes, but this is how you can come up. This it will satisfy this. There is a very specific way to do Hamming code, but there is a reason why they do it that way. So
Yes. So my
there is something called a Gilbert Varshimov bound. It will tell you about the quality of the code that you have. What is the maximum distance you can achieve, and what is the best way you can cover all the messages. So if your code word achieves the Gilbert Varshimov bound, then you can't do anything better. Hamming codes achieve this bound.
Yes, and there are perfect codes as well, and probably
Yes,
which follows the
perfect
Gilbert Varshimov up with the equality thing. I guess.
Exactly, perfect codes.
Yes. Yeah.
Okay.
Yeah. I understood. Yeah.
Yes. So I had other questions also planned, which are quite interesting. So I'll be uploading these questions also in the drive. Okay, please look at these questions. These are some very interesting applications of linear. Especially, I wanted to do question 3 about this what is called Shami's secrets sharing. Okay, this question 3 is actually a really nice application of linear. Very simple also to understand, and very nice application of linear algebra. But yeah, it's already 12:16. I don't think I'll be able to cover it. But if you don't, if you are interested, then you can look it up over the internet.
Okay, sir.
Yeah.
Thank you. The problems are really very nice and very diverse that you chose today.
Okay, thanks.
They are really nice, and
Thank you.
I'll be missing your classes, sir. Yeah.
Oh yeah. I'll be missing you guys. Have you guys in my class also. Oh, by the way, I probably Goel, this will be the last time I'll be offering NPTEL sessions. Next year, I don't think I have a requirement. Okay. So I probably won't be offering any courses. I mean, problem solving sessions.
No issues. Then it shows that probably you are at the verge of completing your degree. All the very best to you for your future things.
Thank you. Thank you. Thank you. Yeah. By the way, you're in the corporate or you're in academics?
Yeah, so I teach in a college, so I'm into academics.
Yeah. Oh, nice. Okay, good. Okay, good to know that. Yeah.
We will keep in touch, and so I mean, thank you so very much for making so much effort. I mean, in these 12-week sessions, and I learned a lot from your sessions. Yeah,
thank you.
And my interest, and you really ignite my interest in this area. Thank you so very much for making so much effort.
Yeah,
I'll be in touch with you.
Thank you. I'll make sure to keep in touch with you too. Yeah, I'm glad you like the lessons, and I mean this time it was the first time for me also conducting problem sessions for this particular course, and I don't work in this area per se. Sometimes there are some applications of linear algebra. So it honestly it was a great learning experience for me also. I also got to learn a few things that I did not know earlier, or some things I had known earlier, but I had already forgotten a long time ago. So yeah, this was a good teaching opportunity for me. I'm just upset that I could not conduct the class on that slot, so that everyone would be there. But I'm glad like you, Rohan, and Satinder were here for the final week. Or in fact, actually, I should be glad, because until yesterday I was planning to conduct just a recording since I had no way of informing. I was just planning to conduct a recording and speak to myself, which would have been actually a bad experience without any interaction. But yeah, you guys have been very receptive from your end also. So I'm very happy for that. Okay. So yeah, I wish you all good luck for everything that you'll pursue later. Okay. And I hope that Rohan.
Yeah. No. Continue, sir. Sorry.
Yeah. I just that's it. I just said I hope that you guys will do well in whatever you're pursuing right now or planning to pursue. So, and I hope that you will keep sharing this love for mathematics. Okay.
Thank you so very much. Thanks,
sir.
everyone. Bye.
Okay.
So just one thing. So after solving this sheet, if we encounter any problem, can I mail it to you or like?
Sure. I won't mind.
Can we talk after this?
Yeah.
Can we talk even after like this session is ending? But can I mail you afterwards? Like
Sure.
if some problem related discussion is there.
Yeah. I won't mind, of course. And in fact, I'll encourage that. And but if there are any issues, just let me know. Okay, and just mail me. I may not reply immediately, but I will reply eventually. Don't worry.
No. It's definitely fine, sir. No problem with that.
Okay, great. Yeah.
Thank you very much, sir.
Thanks.
Okay, thank you, Rohan.
Thanks.
Thank you, Goel. Okay.
Bye. Bye.
Thank you, everyone. Bye.
Okay, thank you.
Oh, yeah.
Bye. Okay, Sachin.
Satinder is saying, sir, can you stop that recording? I think otherwise it will be lengthy.
Oh yeah. Okay.